Energy enthalpy and PV work. In chemistry, we are interested mainly in two types of work: electrical work and mechanical work done by expanding gases. We focus here on the latter, called pressure volume or PV work. Expanding gases in the cylinder of an automobile engine do PV work on the piston. This work eventually turns the wheels. Expanding gases from an open reaction vessel do PV work on the atmosphere. This work accomplishes nothing in a practical sense, but we must keep track of all work, useful or not, when monitoring energy changes in a system. Let's consider a gas confined to a cylinder with a movable piston of cross-sectional area A. A downward force F acts on the piston. The pressure P on the gas is the force per area. We assume that the piston is massless and that the only pressure acting on it is the atmospheric pressure that is due to Earth's atmosphere, which we assume to be constant. Suppose the gas expands and the piston moves a distance delta H. The magnitude of the work done by the system is force times distance, or in this case, F times delta H. We can rearrange the definition of pressure, which is equal to force divided by area, to force equals pressure times area. The volume change, delta V, resulting from the movement of the piston is the product of the cross-sectional area of the piston and the distance it moves. Delta V equals A times delta H. We can then say the magnitude of the work is equal to P times delta V. Because the system does work on the surroundings, the work is a negative quantity. Work equals negative P delta V. Now, if PV work is the only work that can be done, we can substitute into the equation and get delta E equals Q minus P delta V. When a reaction is carried out in a constant volume container, therefore delta V equals 0, the heat transferred equals the change in internal energy. So delta E will equal the heat at constant volume. Most reactions are run under constant pressure, so that the equation will then become heat at constant pressure equals the change in energy of the system plus P delta V. In summary, the change in internal energy is equal to the heat gained or lost at constant volume, and the change in enthalpy is equal to the heat gained or lost at constant pressure. The difference between delta E and delta H is the amount of PV work done by the system when the process occurs at constant pressure, negative P delta V. The volume change accompanying many reactions is close to 0, which makes P delta V, and therefore the difference between delta E and delta H, small. Under most circumstances, it is generally satisfactory to use delta H as the measure of energy changes during most chemical processes. We can measure the work done by the gas if the reaction is done in a vessel that has been fitted with a piston. The piston moves up or down to maintain a constant pressure in the vessel. If we assume for simplicity that the piston has no mass, the pressure in the apparatus is the same as atmospheric pressure. As this reaction proceeds, hydrogen gas forms and the piston rises. The gas within the flask is thus doing work on the surroundings by lifting the piston against the force of atmospheric pressure. If a process takes place at constant pressure, as the majority of processes we study do, and the only work done is this pressure volume work, we can account for heat flow during the process by measuring the enthalpy of the system. Enthalpy is the internal energy plus the product of pressure and volume. When the system changes at constant pressure, the change in enthalpy, delta H, is equal to delta E plus PV, which can also be written this way. Since delta E equals heat plus work, and work equals negative P delta V, we can substitute these into the enthalpy expression. Therefore, delta H is equal to Q plus W minus W, or just Q. So at constant pressure, the change in enthalpy is the heat gained or lost. Endothermicity and exothermicity. A process is endothermic when the enthalpy is positive. A process is exothermic when the enthalpy is negative. Again, when heat is absorbed by the system, we have a positive enthalpy, and when heat is released, we have a negative enthalpy. Exercise 5.3, determining the sign of delta H. Indicate the sign of the enthalpy change, delta H, in each of the following processes carried out under atmospheric pressure, and indicate whether the process is exothermic or endothermic. A. An ice cube melts. In A, the water that makes up the ice cube is the system. The ice cube absorbs heat from the surroundings as it melts, so enthalpy is positive and the process is endothermic. B. 1 gram of butane is combusted in sufficient oxygen to give complete combustion to carbon dioxide and water. In B, the system is the 1 gram of butane and the oxygen required to combust it. The combustion of butane in oxygen gives off heat, so enthalpy is negative and the process is exothermic. For practice, suppose we confine 1 gram of butane and sufficient oxygen to completely combust it in a cylinder, like that in figure 512. The cylinder is perfectly insulating, so no heat can escape to the surroundings. A spark initiates combustion of the butane, which forms carbon dioxide and water. If we use this apparatus to measure the enthalpy change in the reaction, would the piston rise, fall, or stay the same? The piston must move to maintain a constant pressure in the cylinder. The products contain more molecules of gas than the reactants, as shown by the coefficients in the balanced chemical equation. As a result, the piston would rise to make room for the additional molecules of gas. Heat is given off, so the piston would also rise in an additional amount to accommodate the expansion of the gases because of the temperature increase.